So we're recording. Welcome back, everybody. We're about to finish the 13th week of class, and this is the last day that will be on this gravity lecture. Next week, we're going to cover momentum. We'll actually still cover that the week after, so 2 weeks on momentum, and then our third test, then a review, then the final. That's what's going on. So if you recall, the part of the lecture here that we left off on was gravity near the surface of the Earth, okay? And so far, we've been kind of simplifying the picture by assuming that Earth's gravitational field is uniform. In other words, we kind of assume that there's a uniform value of 9.8 meters per second squared for lowercase g all over the surface of the Earth. In reality, that's not quite correct, okay? So, in other words, g is not uniform. So let me explain a few different ways this is the case. So rather than being a constant, the value of little g varies from place to place over the surface of the Earth. One of those reasons, actually, is that the Earth is not a perfect sphere. Okay, so everything we've been dealing with so far when it comes to gravity is assuming perfectly spherical bodies. The Earth is pretty close to a perfect sphere, but not quite. Okay, so for one, the Earth is not perfectly smooth. It has mountains, has valleys, and all kinds of features on its surface. That makes it not perfectly spherical. Another thing is that the Earth actually bulges out at the equator. Because the Earth is spinning, it causes the Earth to actually bulge at the equator. This picture is a little bit exaggerated, but basically what you see here is what the Earth would look like if it were non-rotating. And then this is the Earth when it is rotating and bulging at the equator. Okay, the effect is a little exaggerated, but it is a real effect. All right, and then the last thing here is that the composition of the Earth is not uniform. Okay, so if we think about what's under our feet right now, we could have different types of minerals, rocks, maybe oil deposits. These all have different densities, so they all have slightly different gravitational pulls. That can affect the value of g, okay? So on the whole, g doesn't vary by that much less than 1% from place to place on the Earth, but it is something that does vary a little bit, okay? So what we'll do next is talk about some of those variations and how to quantify them. So let's start with this. The strength of Earth's gravity is going to decrease with height. We know from the law of gravitation that the force of gravity has an inverse square relationship with distance, right? It's a 1 over r squared. So as r gets bigger, that's your distance from the center of the Earth. As that gets bigger, the force of gravity will decrease a little bit. So what I want you to do here is try to estimate the value of lowercase g at the top of Mount Everest. Here's some data that you'll need to do this. Mount Everest has a peak height of 8.848 kilometers above sea level. Okay, so to do this calculation, basically assume that Mount Everest is just sitting on top of a perfect sphere, so that if you're on top of Mount Everest, you're just a little bit further away from the center of the Earth, right? By this much. Okay, the radius of the Earth is right here, 6,371 kilometers. The mass of Earth is right here. Now, this is going to be, again, slightly less than the value we're used to of 9.8 meters per second squared, but you'll have to give it to 3 decimal places to actually see the difference, okay? So when you do this calculation, try rounding to 3 decimal places, okay? So remember, we had a formula we derived for lowercase g. Look back in your notes, use that. Just use the slightly bigger radius and see what you get.
You have to convert the kilometers.
Yeah, you're going to want to have kilometers converted to meters. this problem. Don't forget to square the R in the bottom. All right, does anybody have an estimate? You get something a little bit less than 9.8.
9.786.
9.786, that's what you should be getting. Let's go through that. All right, so I'm just gonna grab a result that we derived in the previous lecture, which is that if you have a spherical body, the acceleration due to gravity on that body, which we denote as lowercase g, is equal to big G, big M, that's the mass of the spherical body, divided by r squared. So here's the picture you should have in mind. Here's the Earth, here's Mount Everest, and we are standing on top of it. So we're a little bit further away from the center of the Earth than if we were at sea level, okay? Basically that means I'm gonna have to add this height of Mount Everest to the radius of the Earth here to get the full distance from the center. That make sense? So here we have, for big G, that's 6.67, 10 to the minus 11, newtons meters squared over kilograms squared. Actually, let me just do this on the next line so I don't run into my picture. So I have 6.67, 10 to the minus 11, newtons meters squared per kilogram squared. Mass of the Earth goes in here, that's going to be 5.972, 10 to the 24 power kilograms. And then here we have the radius squared. So here's what I'm going to do for that. I'm going to take the radius of the Earth, which is 6,371 kilometers, but I'm going to add to that the height of Mount Everest, which is 8.848, also in kilometers. I want this to be in meters, so when I add these two to get my total distance from the center, I multiply by 10 to the 3 to get it into units of meters. And that whole thing down there is being squared, okay? You crunch these numbers, and what you get is 9.786 meters per second squared. So gravity is slightly weaker on the top of Mount Everest compared to sea level, okay? That means it would be easier to jump high at that sort of altitude, right? But not by much, okay? Any questions on this? So yeah, I'm not capable of doing a dunk here on at sea level, but if I were on top of Mount Everest, I bet you could do a slam dunk. Okay. So here's another effect of Earth's rotation. Basically, or here's another way, I should say, that gravity can vary from place to place on the Earth, and that's the fact that Earth itself is rotating, okay? So what I want you to imagine is that we're on the we're not on the North Pole, we're on the equator, okay? We're on the equator of the Earth, and we're standing on a scale, okay? Now the reason I'm choosing the equator is because this is actually where you're moving the fastest in that rotation, okay? Because if we think about it, the Earth, it rotates on its axis once every 24 hours, right? If I'm like down here by the South Pole, the circle I'm moving as the Earth rotates is actually pretty small. I move a pretty small distance every day, so my speed is pretty small, right? On the other hand, if I'm at the equator, I'm moving in the biggest possible circle, so I'm moving the fastest. So that's where we're going to focus our attention, okay? That make sense? All right, so we're at the equator, we're standing on a scale, and there are two forces acting on our body, right? We've got the force of Earth's gravity, that's going to be pulling us in like this. But we also have a normal force, right? Provided by the scale that we're standing on, okay? Now, normally, we would think, well, I'm not accelerating, so gravity and the normal force must balance, right? But that's not quite true, because you're on a rotating Earth. You're moving in a circle, right? So you are accelerating a little bit. And so instead of the forces being perfectly balanced, they're not balanced because you have some acceleration. What direction is that acceleration? It's towards the center of the circle. It's going inwards this way, okay? So what I'm trying to say is this force of gravity going in is a little bit stronger than the normal force going out, so that your total force is something going inwards. That's what's required to be able to move in a circle like this, if you remember. Okay? So what we're going to do is figure out how much different are those two forces when you're standing at the equator. And we're going to find it's about a 3% difference, okay, between the normal force pushing up on your feet and the gravitational force pulling you towards the Earth. So effectively, it's like your apparent weight is a little less when you're on the equator, by about 3%. The reason for that is because of the rotation of the Earth, okay? So again, this is just another subtle effect where gravity is a little effectively different from place to place. So, okay, that's the picture. Let's work it out. Let's do the calculation. So just going off that same picture, you're standing on the Earth, right at the equator. So the Earth is rotating like this about its axis, and you are standing right here on the equator. So you're moving in the biggest possible circle compared to any other place you could stand on the Earth, okay? Now, let's draw that diagram once again of the forces. You have gravity going in, and you have the normal force going out. So I'll just write those as Fg, Fn. Okay? So what we're going to do now is apply Newton's second law to your body, basically. We'll say F equals ma applied to your body. So since you're moving in a circle, right, if you're standing on a rotating Earth, you're moving in a circle, we'll do this for the radial direction. So the net force in the radial direction equals mass times acceleration in the radial direction. So remember how this works? We have Fg going in, that's going to be considered positive. And then we have Fn going out. That's going to be considered negative. Okay, so that's equal to m times a, where the acceleration is v squared over r, if we're talking about circular motion. Okay, so the difference between these two forces that we normally expect to be the same, right, is actually m times v squared over r. Okay? So, I'm going to do a sort of calculation called a percent difference calculation. So we actually have seen this before in lab, right? If I want the percent difference between these two, what I'll do is I'll take the difference, Fg minus Fn, divide by Fg, and multiply by 100. So this is just the definition of the percent difference between these two forces, okay? But here's the thing, Fg minus Fn is something we just determined, right? It's mv squared over r. So I'm just going to plug that into our percent difference calculation. We have mv squared over r. And then for the force of gravity, that's just m times g. M's cancel, and then don't forget to multiply by 100. So here's what we're going to calculate, basically. On top, I have v squared. On the bottom, I have g times r. And then I'm multiplying by 100 to get this to a percentage. All right, so r is just the radius of the Earth. We've seen this before. That's a number I'm just going to plug in. V, that's something we haven't actually calculated yet, so we're going to do that. What does V mean? It's how fast are you moving in a circle if you're standing on the equator, okay? All right, let's think about it. What distance do you travel in one rotation of the Earth if you're standing on the equator?
The circumference of the equator.
Yep, just the circumference of the equator, right? You're going to go around one time around the circumference of the Earth, basically, right? That's going to be a 2 pi r distance, and then how much time is that going to involve for one rotation of the Earth?
24 hours.
That's going to involve 24 hours, right? So it's just 2 pi r using the radius of the Earth divided by 24 hours. But also want to make sure to get that in the right unit, right? So here, this is our side calculation. V is 2 pi r divided by t. And t is our period. That's 24 hours. And we did this before, so I'm going to just kind of skip right to the answer. If you convert that to seconds, it's 8.64 10 to the 4 seconds. Basically, just multiply by 60 twice to get to here, okay? So that means our speed is 2 pi. Okay, now I'm going to plug in r. The radius of the Earth in meters is about 6.37 10 to the 6 meters. And we're dividing that by 8.64 10 to the 4 seconds. Now, can someone crunch those numbers for me? This is going to be the speed of your rotation standing on the equator. Yeah, good. 463.2 meters per second. Now, again, this just applies to the equator. We're currently not at the equator, so we move slightly more slowly because we move in a smaller circle each day, right? But this is like the maximum, okay? So here, now we can plug everything in. V, for our percent difference, V is 463.2 meters per second. We're squaring the whole thing. G, let's just take 9.8 as the value. We're not trying to be too precise here. Meters per second squared. And then R is again 6.37, 10 to the 6 meters. And then if you multiply that by 100, you get this percentage. So you can verify this for yourself, but this comes out to 0.3%, okay? So basically, that's how much your apparent weight is changing at the maximum, okay, due to the fact that the Earth is rotating. So again, it's not a huge effect, but again, if you're on the equator, you can actually, jump a little higher due to this effect than you would elsewhere. Okay, so that's that. And that takes us to the next topic, which is Keplers Law. I did mention this at the very beginning of the lecture, like last week. But basically, I'm going to teach you about some physics here that comes even before Isaac Newton, okay? So these are some laws of planetary motion developed in the era just before Isaac Newton came along and discovered the theory of gravity, okay? So we'll talk about this real briefly. And then if we have some time, I'm going to get into some fun topics, on on sort of modern ideas of gravity, okay? So hopefully we can get through this part fairly quickly. All right, so a little bit more history. So we have two people, Johannes Kepler and Tycho Brahe, that we want to look at here. They each lived in the late 1500s to early 1600s. Kepler was a bit younger. Kepler was like the protege of this guy, Tycho Brahe. Tycho had his own observatory where he made very precise measurements of the locations of different planets in the sky and how they move over time. And basically it was like the best data set for planetary motion that existed at the time. And after he died, that data was inherited by Kepler. And Kepler was able to go through all that data and find some patterns, okay? He was really interested in trying to take all this, giant data set and try to figure out, how can I distill it into some simple patterns that I keep repeating over and over again. And so in doing that, Kepler found these three mathematical laws, which every planet in the solar system appears to obey. So the Earth follows these laws, the planet Venus follows these laws, and every other planet in the solar system, okay? So what we'll do is just go over what those three laws are. There's only one of those laws, the third law, where we'll actually make some calculations with it, but we'll do the overview and then a few examples using the third law, okay? All right, let's start with Kepler's first law. So Kepler's first law, again, this is just something he noticed in the data, was that every planet appears to be moving in an elliptical path around the sun, okay? So this is kind of a change of pace from previous ideas, because prior to Kepler, the common thinking was that all planets move in perfect circles, all right? There was sort of a bias in people's thinking to thinking that, planetary bodies should move in perfectly circular paths. But what Kepler showed is they're not quite perfect circles, they're actually ellipses, okay? And an ellipse is basically just a squashed version of a circle, right? So a circle has the exact same radius everywhere. For an ellipse, it's a little bit thinner on one axis and a little bit fatter on the other axis, right? So that's actually the shape that planets move in. That's the path that planets move in as they orbit the sun. Okay, this is a little bit of geometry. Hopefully you remember this from a geometry class. An ellipse is a shape that you can construct by talking about two focal points, F1 and F2. And the idea is, if we define these two focal points, F1 and F2, then any point on the ellipse has the same combined distance between the two focal points. So in other words, if I take the distance from F1 to this point, the distance from F2 to that point, and sum them together, I'll get the same exact result as any other place on the ellipse. Okay, so the sum of these two distances just stays the same throughout the entire ellipse. All right? So the sun happens to be located at one of those focal points of the orbit. Okay? Another thing we're going to talk about that's going to come up later is something called the semi-major axis. Okay? This is just like radius, but for ellipses. Okay, you can think of it that way. Remember, radius for a perfect circle is just your distance from the center to the actual edge of the circle. For an ellipse, we can't really define a radius because we're not the same distance away from the center, right, at each point. So basically, here's how we talk about the semi-major axis. Every ellipse is going to have like a widest side, right? There's going to be like a widest distance across it. In this case, it's from here to here, right? That's the longest side. The semi-major axis is just half of that longest side. That's all it is. And we call this S, all right, for semi-major axis. I'm going to show you a little demo, actually. I'm not sure if you've seen this before, but basically, you can draw an ellipse by putting two little push pins into a cork board and then looping a string around those, and then taking a pen and just following around like this with the loop, okay? Because think about it, each one of these pins represents a focal point, right? What we're saying is for an ellipse, your distance to each focal point when you add them together stays the same, right? By making the path follow this string, I'm basically ensuring that the sum of the distance from here to here and here to here stays the same, because the length of string I'm working with has to stay the same. You guys see that? So the sum of these two distances as I move around has to stay the same. So I'll show you what happens when I draw this on the paper. And so hopefully, okay, you see this whole thing, it's good. So here, I'm going to put the pen right there. Just follow along like this. Okay, not perfect, but there's an ellipse, right? It's just like a fatter version of a circle. By the way, if I make my focal points wider, space them apart more, then I'll get a more elongated ellipse. If I put them closer together, then I'll get something that's closer to a circle, okay? So let's try to make a really elongated ellipse. How about that? Okay, so put the two focal points really far apart. Something like this. Yeah, that looks pretty good. Okay. Oops. Okay, here we go. Nope. Okay, there we go. Okay, so you see, I put the focal points further apart and I got a more elongated ellipse. Okay. So it turns out for the type of ellipses that planets move in, they're not that elongated. They're pretty close to circular, okay? Pretty close to circular. All right, so that's the first law. Planets move in ellipses, but in reality, they're not that elongated. They're pretty close to circular. Okay, here's the second law that Kepler discovered. This one is basically to summarize equal areas in equal times. So let's think about a planet that's moving around the sun. And let's think about a line going from the sun to that planet. You can imagine that the line is sweeping out some sort of area. You see, like if the planet goes from here to here, this shaded gray region is the area that we sweep out. The planet goes from here to here, from 1 to 2. This is the area that we sweep out. So basically what the third law is saying is that that line drawn from the planet to the sun sweeps out equal areas in equal times. Okay? So let's again take these two pictures here. If we go from 1 to 2, and that takes a certain amount of time, let's say, I don't know, 20 days. And then we go over here from 3 to 4, and that takes the same amount of time, let's say 20 days. That automatically means these two areas are the same, okay? That's how Kepler sort of described this idea. But there's a probably more intuitive way to see it, which is this. Basically, a planet is going to speed up the closer it is to the sun, and it's going to slow down the further away it is from the sun. So let's think about that, right? Going from 1 to 2, we're very, very close to the sun. Going from 3 to 4, we're very far away, okay? So basically, I can get a pretty big area moving from 3 to 4, even if I don't move that great of a distance, just because I'm so far away from the sun, right? Whereas, if I'm going from 1 to 2, I have to move a pretty big distance to get a big area because I'm so close to the sun, right? So the idea is if we're doing equal areas in equal times, I'm going to have to be moving faster when I'm closer to the sun compared to when I'm further away. Okay, so that's how planets speed up and slow down in their orbits. Okay. Any questions on that? All right, then finally we're going to get to the third law. So the first two, I just presented them, but we're not really going to do any sort of calculation with those. The third law, we're going to do some calculations with this. Okay, so let's first put it in words and then try to put it in a more understandable way. So this is what Kepler had to say about his third law. The square of the orbital period of a planet is proportional to the cube of the semi-major axis of its orbit. Okay, a lot going on there. So period, remember, that's capital T. What is the meaning of a period? That's how long it takes the planet to orbit the sun one time. Okay? What's the semi-major axis? Well, it's basically telling you how large of an orbit the planet has, right? It's telling you how big of an orbit is it moving in. Small semi-major axes, planets are very close to the sun. Larger semi-major axes, the planets are really far away, okay? So it's basically a relationship between how long it takes a planet to go around the sun and how big its orbit is, right? That's how you want to think about it. So what we have is t squared is directly proportional to s cubed. Another way you could say that is t squared is some kind of constant value times s cubed, okay? Right, that's what it means for these to be proportional, right? Just a constant times s cubed. Another way we could say that, if you just rearrange this, is that if I put the s cubed on the bottom over here, t squared over s cubed is some kind of constant. So the way we actually use this in practice, okay, in the problems that we do, is we're comparing two planets in our solar system. Like take any two planets you want. Compare the Earth and Jupiter. You can compare Venus and Mars. Just any two planets, right? And this number, t squared over s cubed, has to be the same for any planet you pick, right? So what we can do is like set them equal to each other, right? So let's label one of the planets with subscript 1, right? I have t1 squared over s1 cubed. Just pick any other planet, label it with subscript 2. I have t2 squared over s2 cubed. I know they have to be equal according to Kepler's third law. So typically what we do is this kind of comparison between two planets. That's how we use it, okay? So let me show you real quick where that comes from. I can actually derive this one for you. It's pretty straightforward. So let's get into that derivation. All right, so here is a real quick proof of Kepler's third law. And I'm just going to use circular orbits. So it turns out the math gets a little messy when you actually start doing calculations with elliptical orbits. Circular orbits are much more simple to analyze. So we'll get the result for a circular orbit, but it actually does apply across the board to any type of orbit. All right? So here's what we'll start with. We are imagining some planet going around the sun in a circular orbit. So we apply Newton's second law to that planet, which says the net force is equal to m times a, and we're doing it in the radial direction as we typically do, okay? What's the only force that's going to be present on an orbiting planet? It's basically going to be the pull of the sun's gravity, okay? That's by far going to be the dominant force, so we're just going to pretend like the only thing present is the pull of the sun's gravity. Okay? What is that force given by? Big G, big M, little m over r squared. So remember, big M in this case will be the sun. Little m is going to be whatever planet is going around the sun. Okay? That's how we talk about these two masses. Okay, then on the other side I have the mass little m times v squared divided by r, because that's the acceleration for something moving in a circle. Cancel out the little m's like this. Cancel one factor of r like that. And we get v squared equals big G, big M, divided by r, okay? So you've probably seen that before, right? All right, here's something else we'll do. I'm going to try to bring the period into the equation, right? Kepler's third law involves period, how long it takes to go around the sun. So for that, just remind you that the speed of our orbit is 2 pi r divided by t. It's saying that how fast we're moving is the distance we cover, which is 2 pi r, divided by the time, which is capital T, the period. All right, and then I'm going to plug that v into here. So I have 2 pi r divided by t, square the whole thing. So that's v squared, equals gm divided by r. All right? And what we're going to do next is just shuffle things around. It's pretty much right there. So here, let's square everything in the parentheses. That's 4 pi squared. 2 squared is 4, pi squared right there. And we have r squared. And then on the bottom we have t squared. And then we have g big M divided by r. Okay, so check this out. I'm going to take this factor of r and multiply on both sides, which puts it up here. It puts it up here as r cubed. On the bottom we have t squared. And then I'm just going to divide out this 4 pi thing. 4 pi squared thing, I should say. And there it is. Okay, so what does this say? The radius of the orbit to the third power divided by the period to the second power equals this. And what you should notice about this right here is it's just a bunch of constants. Right? 4 pi, those are constants. Big G is a constant. And big M, as long as we're talking about planets orbiting the sun's mass is just constant, right? So of course, if we're talking about planets orbiting a different star, right, it would be a different constant. But as long as we're talking about planets in the solar system, which are orbiting our sun, then this quantity is going to be a constant. And that's really where Kepler's third law comes from, okay? So again, strictly speaking, we proved it for circular orbits, but it actually applies to elliptical orbits as well, okay? So it's a little bit more general than this. That's where it comes from. All right, now let's do a few examples of calculating things with Kepler's third law, okay? So the first one, we'll do this one together, and then I'll give you one to try out on your own, okay? All right, so here's what we have. A year on Earth and a year on Mars are not the same. How do we define a year? It's just how long it takes the Earth to go around the sun, right? Well, if you're on Mars, it takes longer to go around the sun compared to the Earth. So in that sense, a year is different, right? So it turns out on Mars, the planet orbits the sun once every 697 Earth days, right? Whereas, of course, on Earth, we rotate around the sun, we orbit around the sun every 365 days. For Earth, the average distance of our orbit is 93 million miles. That's how far away, on average, the Earth is from the sun, okay? So based on all of that data, we should be able to use Kepler's third law to find the average distance for Mars's orbit. In other words, how far away is Mars from the sun? We can do that just by comparing its orbit to that of Earth, okay? So here, let's think about this. The way we typically write Kepler's third law is we compare two different planets, okay? And the ratio of t squared divided by s cubed is the same for those two different planets. So basically, we're going to write this ratio down for Earth. We're going to write it down for Mars. And we're going to set them equal. The only unknown quantity is S for the planet Mars, right? We know S, that's the distance for the planet Earth. We know the two periods, that's given right here. So we can solve, all right? So let's go through that calculation. So I'm going to write this one like this. I'm going to say T Earth squared divided by S Earth cubed equals T Mars squared divided by S Mars cubed. All right, it's probably easier just to write it that way rather than saying 1 and 2, because I might lose track of which one is 1 and which one is 2, right? So let's do it like this. I'm trying to find that variable right there, the distance of Mars's orbit, Sm. So Sm cubed, we can actually solve for that. What we'll get is Sm cubed equals Se cubed times Tm squared over Te squared. I think I got that right. Just reshuffling the terms, that's what we get, right? Okay, I'm not trying to solve for Sm cubed. I just want Sm all on its own. What should I do?
Cube root.
I should probably take the cubed root. Now, especially for Kepler's third law, I want to encourage you to try this. Think of taking the cubed root as raising to the 1/3 power, okay? So, just side note, when you take the cubed root, that's the same as raising to the 1/3 power. It's useful to look at it this way. All right, so, actually, if I take this side of the equation, Sm cubed, and I raise it to the 1/3 power, hopefully you see that the powers multiply. I have 3 times a third, and I just get a power of 1. That's why this actually works. That's one way to see it, at least. Okay? But I have to do that same exact thing on the other side, okay? So I have to take this whole thing, Se cubed times Tm over Te. That whole thing is being squared. I have to take that whole thing to the 1/3 power, okay? So to solve for what I want, I'm going to take this whole thing to the 1/3 power, all right? Okay, so I have Se cubed to the 1/3 power, that's just Se. And then I have Tm over Te squared, but then taken to the 1/3 power. So I can write that as Tm over Te to the power of 2/3. You see, that's how this works. You just multiply the powers. Okay? So we all good on the math here? It's not something we talked about in class yet, but hopefully you've seen it before. Okay, let's put the numbers in. For Se, that's going to be the distance for Earth's orbit. We found, or we were given that this is 93 million miles. So 93 million is 93 times 10 to the 6, and then the units are miles. Okay, for Tm, that's the period of Mars's orbit. That's what we were given as 697 days. For Te, that's the period of Earth's orbit. That's 365 days. So days cancel. We don't need to worry about that, right? We're just taking that ratio to the 2/3 power and multiplying by this distance. Can someone tell me what that works out to? 1.77 times 10 to the 7. That's not what I'm getting. You should be getting 143 times 10 to the 6 miles, okay? Or we could write this as 143 million miles. That's how far Mars is from the sun. So it's like 1.5 times as far from the sun as Earth is from the sun, okay? That's why the climate is much colder on Mars, okay? Any questions on that? So, yeah, just got to get used to working with fractional powers here, but otherwise, hopefully it's fairly straightforward. So, let's do this one. This one's for you to work out. So we're using Kepler's third law again, which means we're sort of comparing the orbits of two planets in the solar system. Excuse me. So the Earth orbits the Sun at an average distance of 93 million miles. The planet Neptune orbits the Sun at an average distance of 2.79 billion miles. Okay? So use Kepler's third law to find the period of Neptune's orbit. So you're going to solve for t for Neptune's orbit. For this one, give your answer in years. Okay? If you give it in days, it's just going to be too large of a number to really make sense of. It's a really long orbit, so we'll measure it in years. Okay? So try it out, see what you get. And of course, the t value for Earth is going to be 1 year. Right? So a million is 10 to the 6. Do you guys remember what a billion is as a power of 10? Yeah, it's 10 to the 9. few people got it. A few of you are pretty close. You just need to punch the numbers in. The answer is 164 years. Okay, so that's how long it takes the planet Neptune to go in one full orbit around the sun. Okay, so here's how we can make that calculation using Kepler's third law. So again, the starting point is the same. We have t squared divided by s cubed, and we apply this ratio to two different bodies in the solar system. It's probably easiest to compare things to the Earth because we can remember those numbers because they're the most relevant to us. So we have TE divided by SE cubed. But what we're going to do is set that equal to TN squared divided by SN cubed. So that's that ratio as it applies to the planet Neptune. And again, the ratio has to be the same because we're both orbiting the same mass. All right? So solving for Tn, start with this. Tn squared equals Te squared times times Sn cubed divided by Se cubed, right? All right, so here's what I'm going to do. I'm going to take both sides to the 1/2 power. It's the same as square rooting, but I like to think of this as the 1/2 power. So on this side, what do we have? We have Tn squared, but we're taking it to the 1/2 power. 2 times 1/2 is 1. So that's Tn to the first power, which is exactly what we want, right? But we have to do that on this side, right? So that's going to be Te squared times this, which is Sn over Se to the third power. And then we're taking that whole side of the equation to the 1/2 power. You can think of it as a square root, same thing, right? So what do we have? Te squared to the 1/2 power just gives us Te. Then if we have Sn divided by Se to the third power, and then we take that to the 1/2 power, that's the same as the 3/2 power, okay? So that's what we have. Kind of looks like Tennessee. All right, so Te is 1 year, right? That's the period of Earth's orbit. Sn, that's the distance of Neptune's orbit. That's 2.79 billion miles, so it's 10 to the 9 miles. Okay, Se, that's 93 million miles, it's 10 to the 6. And we take that to the 3/2 power. So you do this calculation, you get 164 years. Okay? Any questions on that? Pretty much the same thing as before, we're just solving for some different variables. And that's pretty much all we need to know about Kepler's laws. All right? That's all we're going to do in this class, at least. Okay? So here, looks like we've got about 25 minutes left. So I thought I'd take this time to go over some modern ideas of gravity. Okay? So just so you know, this part is just for fun. None of this is going to be on the test or any upcoming quizzes, all right? But I think it's interesting because you've probably seen a bunch of sci-fi movies like Interstellar, where some of these ideas actually come up. So they may be things you've heard of before, which we can talk about. Okay. So when we look at Newton's law of universal gravitation, it describes how any massive object in the universe exerts a gravitational force, right? It's given by G, M divided by R squared. Now, that is a really powerful equation because with that one equation alone, we're able to do so much with it. We're able to describe the motion of the Earth, the motion of the moon, and pretty much all other objects in the solar system. It makes complete sense when we have Newton's law of gravitation. It can do some other things if you really get into the math, like explaining the tides. Okay, the fact that when you're looking at large bodies of water, they have tides that come in and out periodically throughout the day. That's actually an effect of the moon's gravity on the Earth, and it's perfectly explained by Newton's law of gravitation. Okay. We wouldn't be able to send rockets and satellites into space if we didn't know about this law. We need to know how their orbits are going to behave and how they're predictable based on this law. And also, kind of more cutting edge stuff that you can do with this law is you can detect objects that can't be observed directly. I mean, let's think about this. If you take a telescope, you look out into the night sky, some things are obvious, like stars. You're receiving their light directly, right? Turns out there's a lot of stuff in the universe that doesn't emit light, so you can't just observe it directly. I'm talking about things like dark matter or planets that are there but are too faint to be seen. Okay, so the planet Neptune was actually discovered this way. Its presence was calculated before it was actually seen for the first time based on this law. And then once telescopes got better, we were able to actually see it for the first time. Black holes, these are objects that don't emit light, but they have an effect on things around them, right? If you have a black hole, you might have a star orbiting that black hole. And if you look out in your telescope at that system, it looks like the star is orbiting nothing, right? If you can measure some of the parameters for that orbit, like what's its period and what's its distance, you could figure out, oh, there's a black hole, it has this mass, all based on the law of universal gravitation. Even things like dark matter, right? These are things you can't see, but you can detect their effects on other objects. If you know the law of gravity, you can find out a lot about these unseen objects, okay? But for all of the successes of this law, there are some problems. So Newton's law of gravity is not the end story as far as gravity is concerned. There are some more modern ideas that have come up since Newton's time. And let me just tell you a little bit about some of that development. Like how do we get from Newton's equation, which is a pretty simple mathematical formula, to the more cutting edge stuff of today. All right, so one kind of problem with Newton's theory is this. Newton's theory implies that if you have two objects, they can be separated by as big of a distance as you want. They still pull on each other. They still exert a force on one another. If you think about every other type of force we've seen so far, it doesn't work that way, does it? Like, if I want to push the stapler, I'm going to have to actually make physical contact with it, right? If I want to lift it up, I'm going to have to make physical contact. I can't exert some action on the stapler at a distance, right? Okay, but gravity does seem to work that way, right? I drop this laser pointer, it's not touching the Earth, but yet the Earth is causing it to fall, right? So every other type of force seems to depend on physical contact, except for gravity, right? Looks like gravity can just happen at a distance, okay? So that's kind of a weird aspect of it that's hinting at something else maybe going on. Another thing about Newton's theory is that it seems to imply that gravity just acts instantaneously, okay? So let's think about this, right? If I take a massive object, I wiggle it around a little bit, that's going to affect something far away, right? It might cause some other mass to wiggle around in response, okay? And that's true if they're right next to each other or if they're on like opposite sides of the universe, right? According to Newton, the effects of gravity are just instantaneous. Like they take no time to travel from one place to another. That's kind of a problem too, okay? Because everything else we know doesn't work that way. If I want to speak to you, I'm going to emit a sound wave, and that sound wave takes some time to get to you, right? If you're going to observe me through light entering your eyes, that light takes some time to travel from me to you, right? Nothing else in physics seems to work this way, where the effect is just instant, okay? And then it turns out there's a lot of problems with that, thinking that, you know, the effect is instantaneous. And so this is a kind of quote that encapsulates this idea. It's kind of written in outdated language, but here's what it says. That one body may act upon another at a distance through a vacuum without the mediation of anything else, and through which their action and force may be conveyed from one to another, is to me such a great absurdity that I believe that no man who has in philosophic matters a competent faculty of thinking could ever fall into it. Okay, so what that's saying is this idea that gravity just gets transmitted instantaneously, that seems to be an absurd idea. I don't really believe it, okay? So who do you think said that? Can you guess? I don't know. You could just throw out any physicist you might guess said that.
Isn't that Einstein?
That's a good guess. It was actually Newton himself, okay? So Newton, the person who came up with this theory, knew there was something deeply wrong with it, okay? He didn't understand, he never found the final answer as to why it was wrong, but he could identify some problems, like, again, that it seems to imply that gravity is just instantaneously acting across any distance of space. So Newton himself realized that. But yeah, it wasn't until Einstein came along that this was all fixed up, okay? So Einstein didn't come up with that quote, but what he did come up with was the theory of general relativity. Has anyone seen in, I don't know, an article you read, a textbook you read, or maybe some kind of documentary, a picture that looks like this? Yet what you're seeing here is there's some kind of massive object like the Earth, and it's warping space and time around it. Has anyone seen this type of picture before? It's kind of common in popular culture these days, actually. But so basically, this is the basic picture behind general relativity. The idea is that space itself, the space that we live in and inhabit, the three-dimensional space around us, it's not just some kind of backdrop where things happen, okay? It's actually something that's dynamic and changing, okay? So the idea is if you have mass, a massive object, it distorts the space around it, okay? Because the space around it is distorted, it changes the path that objects will move in. So if we think about this satellite, if the Earth is not there, it's happy to just move in a straight path like this. But because of the distortion in space that Earth introduces, now the new path that it takes is circular. It looks like a circular orbit, okay? That's really the explanation of gravity according to Einstein, okay? So that just warping of space and actually warping of time, as it turns out to, okay? So this is Einstein's famous equation. Here's what's going on in it. On this side of the equation, you have some kind of description about how mass is distributed, and energy too, actually, as it turns out, around space. And on this side, you have something describing how space is bent and warped and curved by the presence of that mass. So here's a quote that sums it up pretty nicely. It says, mass tells space-time how to curve, and then space-time tells mass how to move, right? So if you have some mass, it warps the space around it, and that changes the way objects move within that space. It can make things happen like circular orbits, for example. All right, so general relativity, again, this is Einstein's theory. Sometimes we call this GR. I'll tell you a few interesting effects of GR. One of those is something called gravitational lensing. So gravitational lensing is this idea that if you have a massive object, the path that light takes is actually bent by the presence of those massive objects. So one example of that was observed in 1919 during a solar eclipse. Okay, so a solar eclipse is the moon is blocking the sun from our point of view. And when this eclipse was happening, there was a certain star that was known to be behind the sun. Okay, so like imagine this, here's the earth, here's the sun, and here's where the star actually is. It's behind the sun is blocking it from our point of view. So of course, if we look out towards the sun, we should expect to not see it, right? It's literally being blocked. However, because of this effect of gravitational lensing, you can see that star. Okay, even though it's got the sun in front of it, you can see the star because the path that its light takes doesn't just get blocked by the sun, it gets bent around it. Okay? And that's one effect that massive objects have, is bending the path that light takes. And that was the first time it was observed, more than 100 years ago. But basically what that did is it confirmed Einstein's theory was right. Okay? This is something that is only going to come out of Einstein's theory and not any other previous theory. Okay? So I'll show you some pictures of other examples of gravitational lensing. Looks kind of cool, actually. You can, much like a lens that you use to, in your glasses or whatever, it distorts light in some way. Okay? So in these two examples, we have a galaxy whose light is being bent by another galaxy. So this may look kind of very distorted and hard to make out, but this is a spiral galaxy. Have you've seen a picture of a spiral galaxy before? It's in the shape of a disk. We're seeing it kind of edge on, so that the disk is being viewed edge on. Normally that's what it would look like, but because of the gravitational lensing effect, it's incredibly warped. See that? Here's another example of that. This is an image of a really distant galaxy, which is being lensed gravitationally. This is actually just one galaxy. You're just seeing 4 different copies of it because of that gravitational lensing effect. Okay? So there are a lot of examples of this. These are just a few. And you can check out some more of those on this link right here. Okay? All right. Let's just do one more thing. Another weird effect of Einstein's theory is something called gravitational time dilation. And just show of hands, who's seen the movie Interstellar? Probably a lot of you. I'm not going to spoil it. I'm just going to say one thing that happened in the movie. It's not going to spoil it for you, okay? Basically, gravitational lensing is gravitational time dilation is the idea that gravity affects the actual passage of time. Okay, in other words, the stronger your gravitational field, the slower time actually runs. So you can basically do this. You can take a really sensitive clock, like an atomic clock that's incredibly precise, and put one down here at sea level. And then you can put another one up here on top of a mountain. And remember, gravity is slightly weaker on top of this mountain compared to at sea level, right? So normally, we would expect the clocks report the exact same passage of time, because they're precise enough to do that. But it turns out, if you do this and then you compare the clocks, they disagree. So in other words, the clock that's at sea level in a stronger gravitational field is running slower compared to the one that's up there on the mountain, okay? This is a real effect that's been observed, okay? So we're kind of used to time as being this absolute thing, but it turns out time is relative in a lot of ways, okay? And actually, this effect has been measured for tiny, tiny distances. You can put 2 atomic clocks, just a foot in height difference, and measure the time dilation just because of that 1 foot height difference, okay? So, all right, here's what we'll end with. You've probably seen Interstellar, in that movie, you have one person who's hanging out close to a black hole, and then you have another person who's waiting in a spaceship kind of further away from that same black hole. Okay, so obviously the person closer to the black hole is in a much stronger gravitational field. And in the movie, that person aged much, much more slowly than the person back in the spaceship, right? From the person who was down by the black hole's perspective, only a few hours passed. The person in the spaceship, from their perspective, like 20 years passed, right? That's not just science fiction. That's an actual consequence of general relativity. It's a real effect, okay? So we'll end it there. I have some more slides. You can look through them if you're interested, but we'll end it there. Next week, we'll start momentum, okay?